Now that we've spent some time talking about ways that stars can be different, like size, color, temperature, and luminosity, let's spend some time looking at how they move from one stage to another. We'll also review some of what we've talked about before about star formation and the nebular theory. Remember, a star is basically a ball of plasma that is continually undergoing fusion in its core. As it does so, it releases tremendous amounts of energy in all different wavelengths of the electromagnetic spectrum. Remember also that stars are formed from nebulae, clouds of gas and dust in space. Here you see a nice image of one, the hydrogen gas glowing red while dark dust blacks out other areas. Here are a couple of other nebulae. Nebulae is the plural of nebula. You don't say nebulas. They're both classified as emission nebulae, indicating that they are made of high-temperature gas clouds energized by ultraviolet light. They glow red due to abundant hydrogen in the clouds, and these nebulae are sites for ongoing star formation. Here are two more examples of emission nebulae. You may also notice that each of these nebulae carry a designation with a capital M and a number. This indicates that these are Messier objects, structures discovered by Charles Messier in the late 1700s as he searched the sky for comets. Oddly enough, though he was most interested in comets, he's much more well known for his list of non-cometary objects. We'll talk more about Messier and his objects in Unit 4. Here is another image of the Trifid Nebula. In this image, you can see several young stars in the early stages of their formation. As these clouds of gas and dust are pulled together by gravity, the region in the center becomes more compact. A protostar is forming. Proto is Greek for first, as in a star in its first stages. Protostars may look similar to the planet Jupiter seen here. They, like Jupiter, would be composed of hydrogen and helium, but are not yet large enough to produce energy by fusion the way an active star does. Once the core of a protostar reaches 10 million degrees, the process of nuclear fusion begins. This is considered the birth of the star. In this image, you can see a star forming in the nearby Large Magellanic Cloud, a small satellite galaxy of the Milky Way. You should know that this temperature of 10 million degrees is what is required for fusion to turn on in stars. Jupiter is not massive enough for its internal temperature to get this hot. So even though it's made of the right elements, Jupiter can never be a star. As described in the second lecture of this unit, nuclear fusion is how a star produces energy. It combines normal hydrogen atoms into deuterium and tritium atoms. Deuterium and tritium are special, heavier forms of hydrogen. Then, these combine to form helium atoms. It takes 4 regular hydrogen atoms to form a helium atom. For the majority of a star's life, it will fuse hydrogen nuclei into helium. Stars in this stage of hydrogen to helium fusion are called main sequence stars. Our Sun is a main sequence star. Stars the size of our Sun will remain in the main sequence for about 10 billion years. As our Sun is between 4 and 5 billion years old, it is only halfway through its main sequence stage. Remember that fusion occurs in a star's core. Then, the heat and light generated must move outward through the radiative and convective zones of the star before being released into space. However, all the time, gravity is pulling the incredible weight of the star's gas into the center. A star's entire life is a balancing act between the outward pressure of the released energy and the inward pull of gravity. As long as nuclear fusion is occurring, the balance remains intact. However, the star's supply of hydrogen can only survive for so long. Once the hydrogen is gone, fusion stops, and the outward pressure cannot overcome the star's gravity, pulling the mass toward the center. The mass collapses on the core. This collapse causes the temperature to rise. At a higher temperature, fusion can begin again, but this time, instead of fusing hydrogen to helium, helium is fusing to carbon. This stage of fusion requires much higher temperatures and can only occur after this core collapse. Notice here that the giant core temperature is about 10 times hotter than the main sequence core temperature. Having restarted fusion, the star becomes stable again, but it becomes much larger. With increased temperature, the particles move even faster, expanding outward. When our sun reaches this stage, it will consume Mercury, Venus, and probably Earth's orbit. And though the hydrogen burning stage lasted for 10 billion years, the helium burning stage is much shorter, only about 10 million years. Remember, the larger the star, the shorter its lifetime. The process continues. Once the supply of helium is exhausted, the star again becomes unbalanced, collapsing again. This collapse and subsequent rebound releases tremendous amounts of energy. Here, the paths of different types of stars diverges. This is pretty much the same as your star life cycle drawing assignment. At the far left of the diagram, you see the nebula forming the main sequence star. But once the hydrogen to helium and the helium to carbon stages are over, it depends on the size of the original star which path it will take. We're going to start by looking at the evolution of a small to medium-sized star like the Sun, the bottom part of the diagram. Once a Sun-like star finishes fusing hydrogen to helium, it becomes a red giant. The red giant stage continues as long as the helium holds out, being fused to carbon and maybe some oxygen. But at that point, the star's second gravitational collapse, it will not have the power to continue to fuse elements. Stars like the Sun will form a planetary nebula, as shells of gas are thrown out by the star as it dies. Even though they are called planetary nebula, they have nothing at all to do with planets. The terminology was invented because they often look like planets in telescopes. In the center of the nebula is all that is left of the original star, a small star called a white dwarf. It is called that because it glows white in color and is incredibly small, only about the size of Earth, which is quite small considering how big the star used to be. The white dwarf will slowly radiate out all the remaining heat and light until it has died. Then it is called a black dwarf. Here is an image of a planetary nebula called the Ring Nebula. The white dwarf can be seen as a dot in the center of the nebula. Here's another planetary nebula. Sometimes the gas expelled from the star goes mainly in two directions, forming a dumbbell shape rather than a complete ring. Other planetary nebulae, like the Cat's Eye, have intricate patterns seen in different wavelengths of light. Some patterns are somewhat irregular, like here in the Stingray Nebula. It isn't fully understood why some patterns form so differently than others. And here's one last planetary nebula, the Owl Nebula. Can you see his dark eyes looking at you? The white dwarf within the planetary nebula is inactive. It is not powerful enough to start carbon fusion. It has collapsed in on itself to create a very dense mass about the size of Earth. A tablespoon of white dwarf would weigh 5 tons. It may take thousands of years for the white dwarf to cool. Eventually, the heat and light will fade, and a black dwarf, basically a ball of charcoal out in space, will be all that remains. No more visible light will be released, and only low-energy radio waves will continue to radiate from the black dwarf. It continues to have gravity because it is still a high-mass body. Now, let's look back to our diagram and follow the other path. This is the path taken by stars, which started out much heavier than our Sun. Stars that start out about 10 times larger than our Sun will transition from a red giant to a type of star called a supergiant. Once the giant has fused all the helium to carbon and the core collapses, just like it did with the Sun-sized star. This time, though, there is enough mass to generate sufficient heat inside the massive star to start fusing carbon into heavier and heavier elements, up to and including iron. Here in Orion, we see one of these massive red supergiants. The star Betelgeuse is a red supergiant. It is so large that if we took the Sun out of our solar system and replaced it with Betelgeuse, the star would extend out to the orbit of Jupiter. Some stars will expand even farther and would extend out to the orbit of Uranus if they were in our solar system. It's a good thing that this will never happen to our Sun. Within these huge stars exists a layered structure, where the remaining atoms of the lightest elements are on the outside and the heaviest atoms are found farthest within. The information to the side of the illustration shows how each element is formed. 4 hydrogens make a helium, 3 heliums make a carbon with 1 or 2 more heliums makes oxygen or neon. Neon with another helium or a carbon makes oxygen and magnesium. Oxygens can then make silicons, and silicons make iron. You don't need to memorize all of the steps, but you should know that the first step is what main sequence stars do. The second step is the giants, and then the supergiants can go up as far as iron. Here's an image illustrating the relative abundance of each element, which basically means how much we have of each element in a star. Notice that hydrogen and helium are by far the highest. Notice also that the scale zigzags as it drops down. Even-numbered elements are much more common than odd-numbered elements. Heliums are the basis of anything larger than hydrogen, and since helium is an even-numbered element, so are most other atoms in stars. Now notice the elemental abundances in stars compared to people. Stars are mostly hydrogen and helium, about 1% oxygen, and very little else. All the rest of that last percent is all the rest of the elements. Now look at the human graph. Human beings, mostly water, H2O, are composed of a large amount of hydrogen and oxygen. We also have a lot of carbon, nitrogen, and calcium, those even-numbered elements easily produced in stars. The atoms we are made of literally are produced in stars. As famous astronomer Carl Sagan once said, "We are made of star stuff." After the supernova explosion, there are a couple of different things that can happen. One possibility is that the iron core collapses to form what is called a neutron star. This happens incredibly quickly, in less than a second, with material falling in at about 1/10 the speed of light. This creates the atoms up to uranium, the heaviest naturally occurring element. If you look at the periodic table, you'll see that copper, gold, and silver are heavier elements than iron, but aren't as heavy as uranium. That means that if you wear silver or gold jewelry or even have copper pennies in your pocket, you literally have bits of exploded star in your possession. In these type 2 supernova events, the outer layers of the star are blown away and we see the remaining core, which is quite small, radiating light from radioactive atoms. At this point, the star has no more fuel left to burn. We see tremendous amount of light that can be seen from other galaxies. Sometimes a single supernova can shine brighter than its entire galaxy. Here, you see an image from a supernova that occurred in the year 1054. It's also called Messier Object Number 1 or the Crab Nebula. The nebula you see here is not a nebula where new stars are forming, but the leftover gas and dust from a star that has died. This bright spot shows a supernova explosion that was so bright it was visible to the naked eye. It was spotted in 1987, but the star was so far away that the explosion had actually happened 180,000 years earlier. It just took the light that long to reach the Earth. A star like Betelgeuse will explode in a supernova. It is a supergiant, but it doesn't look all that big to us because it is so far away. In fact, it is hundreds of light years away. That means that even if Betelgeuse exploded right now, humans on Earth wouldn't know for hundreds of years because the light from the explosion would take about 640 years to reach us. That means it's also possible that Betelgeuse may have already exploded and not enough time has yet passed for us to know it. A supernova explosion is incredibly energetic. Let's put some numbers to it. Our sun puts out 90 billion megatons of energy per second. A megaton is 1,000,000 tons. How much energy would that be in human scales? Let's scale the sun down from an AU away to a kilometer away. By that scale, the energy output would be 4 tons per second. That would be equivalent to a truckload of explosives a kilometer away, putting out a 1-second burst of heat and light similar to the sun. A supernova would be brighter by 10 billion times. Instead of a truck with 4 tons of explosives, we'd need 40,000 megatons or 40 billion tons. That would be equal to setting off all the nuclear weapons on this planet every second, and this would continue for days. That's an incredibly awesome amount of energy. As I mentioned, there are different types of supernovae. So far, we've been talking about type 2 supernovae, explosions of massive stars as they die. Another important type of supernova is a type 1A. Notice a really backwards thing about these names. A type 2 supernova is what happens when one really big star dies, but a type 1 supernova actually requires 2 stars. Type 1A supernovae occur when a white dwarf has a companion. Most stars orbit around with a buddy. Our sun is an exception, as it has no companion. When a star like our sun is dying as a white dwarf, if it has a companion, it is sometimes able to steal mass from its friend. It can continue to accrete mass from its friend until it reaches 1.4 times the mass of the sun. At this point, the star reaches what is called the Chandrasekhar limit and becomes unstable. It will explode, and all type 1A supernovae have the exact same luminosity. That means that they can be used to measure distance. If we know how bright an object really is, absolute magnitude, we can compare that to how bright it looks to us, apparent magnitude, and determine how far away the object is. The type of object is called a standard candle. We will talk more about standard candles in the next unit. Once the red giant explodes in a supernova, 2 final possibilities exist for these massive stars. One possibility is called a neutron star. It's called a neutron star because the atoms of the star are compressed by gravity so much that protons and electrons are actually crushed together into neutrons. This neutron star core will survive intact as a body only about 6 miles wide, but with a mass of 3 suns. The rest of the mass was lost to space in the supernova explosion. These neutron stars often spin rapidly, sometimes creating pulsars that act like spinning lighthouses, releasing energy in 2 jets from the poles. Others have incredibly strong magnetic fields and are called magnetars. The other object that can form after the supernova explosion is a black hole, and these may be the strangest objects in the cosmos. If the core of the star that went supernova is heavier than 3 solar masses, the core collapses even further. It is so massive and so dense that its gravity does not even allow light to escape it. Since we can only collect information about objects in space in the form of different wavelengths of light, black holes are hard to study. We cannot collect light from them because even traveling at the speed of light, 186,282 miles per second, it still cannot escape the black hole. The first black hole ever detected was called Cygnus X1 in the constellation of Cygnus. Though we couldn't see the black hole itself, we could see the accretion disk of material that was being stolen by the black hole from a companion star. Sometimes we can even see jets of X-rays being expelled by the black hole. Here you can see the 3 possible pathways ending either in a black dwarf, a neutron star, or a black hole.